All right, folks. Yesterday, I believe we ended on this question where it says a sum of $1,000 invested, interest rate 12%. All interest rates, when you go to a bank, when you go buy a car, go buy a home, they're all, get a credit card, they're all provided as annual interest rates. Okay? So when you are dealing with those things, for instance, if I go to a bank and they give me, let's say, or I go to Edward Jones or whatever, and I've got something that's got a 3% interest rate. Okay, that's an annual interest rate. So if they're going to compound my account over maybe with a compound of, let's say, monthly, I'm not going to experience all 3% every month. Does that make sense? I'm only going to experience 1/12 of that 3% each month. Okay, so that's why when in our formula we have, instead of 1 plus I here, because I being the interest rate, it's R divided by N. It's the amount of the interest rate that you experience during that compounding period. Okay. And then we raise that to the NT, the number of times that it's getting compounded for the duration of the investment. In this situation down here, it says find the amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, and daily. I believe we talked about those being kind of the key compound values. Okay, 1, 2, 4, 12, 365. We could do weekly, bi-weekly, that kind of stuff. But I think when the bell rang yesterday, we were demonstrating this in Desmos, and I urge you to use this because it is so much quicker to evaluate than using anything else. And it's safer because it puts things in the math print for you. But basically all you're going to do is you're going to type in your formula, and we can use this here with, my hopes are that you guys develop a liking for Desmos, because a lot of your stuff beyond this course, and even things that we've dealt with in this course when we're evaluating, they're complex formulas. Okay, even if you're a person that struggles with like the quadratic formula, Desmos is awesome for that. Okay, if you can type in the formula and then below type in your variable, define your variable. So I want my principal to be 1,000 here. I wanted my interest rate to be 12%, and I wanted N. I'll actually put N here. Actually, I'm gonna put N first because we're gonna change it, and just for your guys' view, it makes it a little bit easier. Then R, my interest rate was 0.12, and then T, we said was gonna be 3 years. So I insert those things, and you see once I have all my variables defined, okay, when I don't have them all defined, it tells me that there's a warning, too many variables. Try defining T. So I define T, and now I have them all defined, and it'll actually evaluate it. So what we're finding out here is that if I compound it at the end of every year for 3 years, I'm gonna make, or this is what's gonna be in my account, ultimately making that much money. Okay? So just letting it sit, $1,000 sit, you make almost half of it. Does that make sense? That's pretty lucrative. That's a very high interest rate. But we say, okay, what happens if we compound it semi-annually? So if not using Desmos, you have now a whole nother problem you have to go through. But using Desmos, I just changed the one variable N to 2, and I see that now we have a little bit of growth there of about $14. When it was one compound, it was 0.04, and now it ends in 1.8. So again, $14. Does that make sense? So there we see increase in the number of compounds, increase the amount of money made, right? Okay, which should make sense because now at the 6-month mark, we roll our money over, and basically our money now becomes the new principal, and that money that we earn, the interest that we earn in the first 6 months, is now going to earn interest for us in the second 6 months. When this was a 1, that did not happen. Okay, so then we can change it to quarterly. So we're going to roll it over 4 times after the 3rd month, after the 6th month, the 9th month, and the 12th month. And you see there that it jumps from $14.18 to $14.25. So a $7 increase when we go from 2 compounds to 4. Then we say, well, let's do it monthly. So now that's up to 30. So we've gone from 1404 up now to 1430. So we've made a $26 increase. Okay. And people might say, well, $26, that's not really, that's meaningless maybe in compared to $1,400. But think about having $1 million in there. Now it's $26,000 that is the difference. Does that kind of make sense? Okay. But then again, and these are all things I think are important to talk about. How does $26 compare to $1,000? And how does $26,000 compare to $1 million? Relatively speaking, they're the same, right? So if you stole $26 from me, I'd be pretty upset. Okay? Because $26 to me is a big amount of money. Okay? Steal $26,000 from a millionaire, they should, because of relativity, should have the same upsettedness with you, if that's even a word. Okay? Or disdain for you. Because it's the same percentage. But we find out that, what if we do this weekly, change it to 52? Now we've made more money, right? Now we went from 1430 up to 1432. Let's do it daily. So 365, do it daily. So we went from 1432 when I did it weekly, and now it goes up by, it's not even a full dollar when I do it daily, okay? Let's say we compound it, not daily, but do it twice a day. It goes 0.24 is, so 24 cents, right? That's what we've got up there. And then if I do it twice a day, it goes to 0.28. Okay? What if we do it hourly? It goes from 0.28 to 0.32. Gain 4 cents. Okay? By adding so many more compounds, we only added 4 more cents. Does that make sense, everybody? So initially, 1 compound compared to like 300 compounds, or 1 compound compared to 365 compounds, there's a large jump in the interest made. But when I get to a point of doing like 365 compounds to then doing 8,760 compounds, there's not that big of a jump. Okay? But what we really like to do, what is the best for the consumer, is not just to compound on the hour. Okay? Not to compound on the day or the week or whatever like that. We like to compound instantaneously, meaning that compound it, if I go on the hour here and then do it on the minute, and then compound it on the second, and we can go further, we can break it down to like the millisecond, nanosecond, that kind of thing. But basically what we want to happen, and you see there that we've gone to 31,536 compounds per year. Okay? So if we multiply that by 3, we're getting like 92, 93 million compounds here through the duration of this investment. That is going to be, look at the total up there, it's 1433.329, right? Well, when I was doing it at 365, it was like 1433.28. It wasn't that big of a difference, okay? But the idea here is that we're compounding instantaneously. By the time our money rolls over, it's starting to roll over again. Does that make sense? Okay? So if I put my money in an account in second 2, that money, it's bigger now in second 2 than it was in second 1. Does that make sense? And now that bigger amount, that investment, that interest that was earned between second 1 and second 2 is now going to earn me interest and more money in second 3. And then all of that interest that was earned in second 1, 2, and 3 is going to earn me interest in second 4. And that continues for the duration of the investment. Does that kind of make sense? We call that continuously compounding. And that's what today we're going to get into before we leave. But eventually what we find out is that that number right there, we want that to essentially go to infinity, okay? Which would mean that we're compounding all the time, okay? So that was the type of question we did yesterday using that formula. There is another type of question that you're going to see in your homework that asks you this type of scenario. It says, find the present value of $10,000 if interest is paid at a rate of 9% per year, compounded semi-annually for 3 years. Okay? What we're asking, so present value is a new term here. Okay? Previously the question was find the amount after time t, the amount of the investment after time t. Here it says find the present value of $10,000. What that means is that $10,000 is the amount t. Okay? It's the A of t in the previous question. So basically the idea is I have a need for $10,000 in 3 years from now. Okay? Maybe I know I'm going to retire and I want to buy a boat and I want to buy it with cash. And I know my boat that I'm going to buy is going to be $10,000. Okay? But I don't have $10,000 liquid cash right now. I can't afford that. Does that make sense? But I do have some money. Okay? This question is asking how much money do you need to invest in this account right now so that in 3 years, without you doing anything, it grows to $10,000. Does that make sense? That's what present value is. You see the definition up there. It says present value of a sum of money is the amount that must be invested now at a provided or given rate of interest to produce the desired sum at a later date. So my desired sum at a later date is $10,000. So we have our formula A of t is equal to principal 1 plus r over n raised to the nt, okay? Our desired amount down the road, which is A after a time of 3 years, is $10,000. That's what they mean by that present value term says that's where you're going to put the 10,000 in your formula. We don't know the principal. We don't know the initial investment. That's what I'm trying to figure out here. Okay? But we know everything else. We know the interest rate is 9%. We know we're going to compound semi-annually. And we know we're going to do this for 3 years. Okay? Now, if I really think about this, this 1 plus 0.09 divided by 2 raised to the 6th power, that is what for capital P? I'm just looking at just equation type stuff. That amount is what for that variable P? That evaluates to something, right? And you have, so that evaluated times P, so that has to be a what for P? A coefficient? So what can I do to both sides to solve for P? Divide by that coefficient, right? So if we take 10,000, divide it by 1 plus 0.09, divided by 2, which is just 0.045 if you want to write that way, raised to the 6th power, gives me that number there. So what this tells me then is if I have access to this account, I'm at the bank right now, and they're offering me 9% interest rate, and they're going to compound it twice a year for 3 years. If I want $10,000, then at that moment, I need to fork over to the bank $7,678.96. And then in 3 years, on the minute, in 3 years, I will be able to withdraw $10,000 from that account. Does that make sense? Okay. You can, once you do this in Desmos, this is what I love about it. Remember, that was the formula, right? Okay. I was looking for what amount do I need to put in there. Well, if I put this amount right there for P and evaluate this, so you can do this a couple different ways. You can cut and paste that. So Control C and then just Control V, and you can see that that does then turn into my $10,000, right? Or you can just come up here and say P is equal to that. And then down here where it says P, it's going to plug that number in, and you see that it evaluates out to 10,000 bucks. So it's kind of a check to make sure that this number is correct. Does that make sense? Okay. So that is present value. You're going to see in your homework, if you looked at any of that yet, about a handful of the questions ask something like this, where you're finding the amount after a particular time. And then there's a handful of questions that say, actually solve for the principal given a defined present value. Is that okay? Now, what I want to talk about today is getting into section 4.2. There's going to be some stuff that we, over the next couple days, kind of glaze over that in the past I've spent more time on, but because we're up against the 14th being the last day of the semester, and we've had so many things with starting the school year late, and I missed 2 weeks being quarantined. We missed about 2.5 weeks with no technology, that kind of stuff. We're a little bit behind in regards to, we'll be able to get everything done, but a little bit behind in regards to being able to maybe spend more time on some like little derivations, some ways of, I'm gonna basically give you a formula today, but not prove it with you. Does that make sense? In the past, I would have proven it. I will still provide, I'll provide you that information. You're just gonna have to investigate on your own if you have that interest, okay? There's some stuff in here today that we kind of glaze over. You're just gonna take my word for it. But 4.2 is talking about the natural exponential function. The natural exponential function. It's still a to the x. It's still an exponential function like 2x, 3x, 4x, 5x, 50x. But it's going to be a special one. It's a different base. Okay? And that base that we're going to use is called the number e. Okay? The number e. Referred to several different names for it. Natural number is the most common name. In science, you might hear it called Napier's constant. But the letter E was discovered. Okay, it's an irrational number. It's like pi. Okay, and it was discovered by a guy named Leonard Euler. He's one of the most influential mathematicians of all time, especially for algebra. He was investigating this function here: 1 plus 1 over n raised to the n, or x raised to the x, how you want to write it. But his interest was what happens when n or x, whatever variable you're using, gets very, very large. So he's interested in behavior of this function. Okay? And what he found out is that this function has some asymptotic behavior. Okay? So if I look at, let's see here. 1 plus 1 over x raised to the x. Get our axes back in here, maybe. All right, so what he was interested in, if we're looking at this curve, this is the 1 plus 1 over x raised to the x. He was interested in, as x gets larger, okay, as x goes out greater and greater on the x-axis, what is happening to this y value? So basically, as this number here, this number, and this x-coordinate gets bigger, what is this number getting closer to? So what we do is, if we move this out, we can kind of see that that number obviously getting larger, and it's going to go up to infinity. This number right now it's not growing all that much. It looks like that 2 is pretty static. Okay. If I move all the way out here, still think so that now that 7, that 6 has changed to a 7. And now if you kind of look at things, this number right here is changing. As I move to the right, that 4 is changing. So as that 4 is changing, it goes to 5, goes to 6, up to 9 now. Okay, so now that went to a 1. And now we're going to find out is that number changes. So eventually this one is going to become static at some point. Is that going to make sense? So what we're seeing here is that this number, this y value, as x gets larger and larger, that y value is tending to a number approximately like 2.71-ish. Okay? And what he found out is that it actually, that y value out to 1 million goes to 2.71828. Now, the way he was doing this is through, he didn't have technology. This was centuries ago. So he's doing this by hand using other algebraic principles and concepts. But he found that this number here was going to be never ending and never repeating. So he finds out that this thing, as x gets really, really big, becomes an irrational number. And he identified or labeled that. I don't know if he actually named it E, or, after, a lot of times, like somebody that creates something, they die, and then somebody else reads it, and they honor that person with the name. Does that make sense? Mm-hmm. So I don't know if he said, I'm going to name this after me, or if his colleagues named it after him. But E, the reason we use the letter E is because Euler starts with an E. But that's the number, 2.718281824. Okay. On your calculator in your 28384, it is your LN button. I think you got to hit the second key. So the LN and E to the X, they are tied together, okay? Much like when you see on your calculator x squared and square root, they're tied together. Why is x squared and square root tied together on my calculator? They're what to one another? Inverses, right? X squared and square root undo each other. What do you think then the logic of e to the x and ln are? They're probably inverses, aren't they? Okay, so we'll talk about that in the future as well. So if we look, so E is just a number. It's a real number on our number line, and it falls between 2 and 3, but it's closer to 2. So if we look at an exponential function, like we've been investigating, 2 to the x looks like that, 3 to the x looks like that. So E to the x should look like one of those. It should look like both of them, but be closer to one than the other. And because E is 2.7, so E to the x is going to look, it's going to be that blue one. Does that look like it's closely tied to the red one? Because 2.7 is pretty close to 3, right? Okay. But that blue function is exponential. A lot of times E to the x is referred to as the exponential function. Okay. Or 2 to the x, 3 to the x, they are exponential functions, but a lot of times E to the x is called the exponential. It's like the most prominent exponential function. Okay. People might argue, okay, so, and people argue this all the time about pi being 3.14. Why don't we just make pi 3 and it'd be easier to deal with? It'd be easier to do other calculations. People argue the same thing about, obviously that would screw up a lot of mathematics if we did that. People argue, well, E isn't all that nice of a base to use. 2 or 3 is much easier to use than E. 10 is much easier to use than E. What we're going to find out is that E actually has a lot of real-world applications. Okay. And again, because of time, it's going to be hard to show those things. But what we find out is that E shows up a lot in how populations change, okay? How we'll call logistics or predator-prey models or growth models or decay models, how those things change, E is heavily involved, okay? So this is referred to as a logistics model here. Basically what happens is we can take data from a population and construct it into a model. Okay, so take that data, run through some algebra that will create this function, and we find out that E is part of this function that models the spread of this disease in this small population. Okay, it says an infectious disease begins to spread in a small city of a population of 10,000 people. After T days, the number of people who have succumbed to the virus is modeled by this function. Okay, so we've maybe collected data on these 10 days. All right, so T days. We've collected data after T days. So 1 day, 2 days, 3 days, 4 days, and do some analysis on that. We find that that data fits this model, or this model fits that data. Much like we would do with a parabola or cubic or what have you, whatever type of polynomial function we fit data to. But we see E is involved here, okay? And the question now is, well, how many people are initially infected? Okay, so if we have this, by taking our raw data, creating this, we can now work our way back to data that we didn't have at the beginning, okay? Because we didn't know that the disease was there on day 1. Does that make sense? Or instant 0, I guess, okay? It wasn't maybe until day 2, day 3, day 4 that we actually find out that people are getting sick. So how can we work back to see how many started the infection? So when we say how many people were initially infected, the word initially means the time is 0, right? And that's something that you're going to have to pay attention to in your homework. They're going to use this phrase only. They will not put, so that phrase right there, they will not put t equals 0 for you. You need to know that initially means time is 0. What happens here? Well, what if time is 0? If I plug in 0 for this exponent right here, so that becomes 0, what does that product become up top in my exponent? That becomes 0, right? What's e to the 0? 1. So doesn't that denominator become 5 plus 1245, which is 1250? If I divide those, we get 8. Okay, so what this allows me to say or determine, basically we're extrapolating here, we're finding a value outside of our observed data. Okay, but we observe maybe, like I said, day 1, day 2, day 3, day 4, day 5, day 6. We construct that data, we find a model that fits it, and then we can work our way backwards. Okay, at time 0, at the instant that the disease started spreading, how many people were initially infected? So 8 people started this infection. Does that make sense? Okay. Now, would that mean, like, people, well, doesn't an infection have to start with 1 person? But the idea here is we had 10,000, right? We had a city or a village of 10,000. So maybe these 8 people flew in from somewhere. Does that kind of make sense? Now they came home, or maybe it's a family of 8 that went on vacation. They come home, and now they start spreading that disease within their community. So let's find the number of affected people after 1 day, 2 days, and 5 days. Okay. Again, what I would do on something like that is type in that logistic model. So 10,000 divided by 1245. So it's 5 plus that, right? 5 plus 1245. E raised to the negative 0.97 t. And I'll just, so if t is 0, you can see right there that it does generate 8, so we did that calculation right. If t is 1, okay, so after 1 day, well, there should be about 21 people that are infected. Okay, after 2 days, we should be up to 54. And you're seeing that there's not a, between days, there's not a common difference. Okay, so between 0 and 1, there's like an 8-person difference. Between 1 and 2, there's like a 12 or 11-person difference. So day 2, we've got 54 people infected. Day 3 jumps up to 137. Okay, so day 10 maybe, we're up to almost 2,000 people. Okay, so you see that the growth is happening much faster as T grows, correct? Okay, so we're actually see if we were to plot these times in terms of days compared to the number of people infected, you will see a exponential growth model. See if I can copy this over to a graph. Would you agree that that graph is exponential? Okay. So that's the model that's showing that spread. So diseases, viruses, they spread exponentially like this. All right, so that you're going to see maybe a handful of questions in your homework with those testing, but they'll give you the formula, and then you're just evaluating. So I just wanted to give you a heads up on that. Use Desmos to evaluate, make things a little bit easier yourself. Okay. Going back to our finance type questions, compounding interest. Okay. When we compound interest continuously, it means that by the time that my money rolls over, it is rolling over again. It's always making money, and that new money that has been made is now collecting interest to make more money for me. Okay. When that happens, okay, and I will provide you a printout, or I might just write it over here at some point in the next day or so, the proof of this. But what happens when we look at our formula that we talked about yesterday? Okay, part of this formula, and there's just some creative algebra, this formula here, or that part of the formula, looks a lot like what Euler was looking at when he was investigating and finding E, doesn't it? Okay, now it's different variables, R and N instead of 1 and N. Up here it's N, but it's very similar. And so some convenient algebra I can show you that it basically is going to take out this stuff here when we compound continuously, and it's going to replace it with E to the R. That stuff right there will get replaced with E to the R, and we'll still have that T there. So if I'm compounding something continuously, there's my new formula. Okay? And like I said at the beginning of class, that is something that in previous years we spent a little more time, because I think the algebra, the proof of it is good algebra for you guys to see and to experience. But again, running short on time to do that. Same definitions for our terms here. P is still your principal. E is E. R is your interest rate. And T is your number of years. Okay. So when they ask us a question such as this, it says suppose $5,000 is deposited in an account paying 3%, compounded continuously for 5 years. Find the total amount on the deposit at the end of 5 years. So the key thing now you have to pay attention to in these questions is that they will identify how they want you to compound it. Do they want you to compound it continuously? Because if it does, that elicits that new formula. If they want you to compound daily, monthly, hourly, whatever, that is our previous formula. Okay? So what we do here is we say the amount of T is equal to your principal times E raised to RT. Again, our principal is the 5,000. E is E, okay? It's the 2.7 number. R is 3%. Be careful with this. I get a lot of people say 0.3. It's 0.03. And T is 5 years. And now I'm just going to grab one of our calculators. and we'll put that in. So PE raised to the RT. I'm also going to do here, just so we can see the difference, P1 plus R divided by N raised to the NT. But if I do, so our principal we said was 5,000, right? Our interest rate was 0.03 and time was 5 years. And we see then that if we compound continuously, at the conclusion of those 5 years, we'll have $5,809 in our account. Okay, and that's not a bizarre interest rate. Okay, so that's more appropriate than maybe the previous questions that we've seen in a real life type situation. Now, what I want you guys to see is, okay, well, what if you see the difference here? If this one here was compounded continuously. This one was compounded once a year. Which one made me more money? Continuous, okay? Now, as I compound more, so let's go, I compound maybe weekly. Okay, which one is still more? Top one, right? What if I compound daily? Which one's better? Top one's still better, right? Continuous is still better by 4 cents. But what if I compound hourly? Top one's still better? By less than a cent, but it's still better, okay? If I compound on the minute, top one's still better, okay? And the argument here is that compounding continuously is always better for the consumer because your money that you just earned is going to earn in the first second, is always going to earn you more money than in the second second. Does that kind of make sense, everybody? So you're going to see questions like this that'll say, you know, Bank A offers me 5% compounded weekly. Bank B gives me 5% compounded continuously. What bank do I go with? B. I don't even have to do any algebra, any math. I know continuously compound is better. But not all banks can do that. One bank might say, we give you a 4% interest rate and compound it monthly. Bank 2 might say, we can't give you 4%, we can give you 3.8. But we can compound it continuously. You know continuous is better, but you also know the 4% interest rate was better, right? In that scenario. So in that situation, you have to actually take a principal, invest it in both, okay, or run it through both formulas, and then say, okay, bank 1 or bank 2, which one yielded the higher result, and then that's the one you choose. Does that make sense? Okay. And in that situation, it doesn't matter what your principal is. Okay? If Jackson wants to invest $1, but Haley wants to invest $10,000, it's still going to be relative. Okay? Bank 1 or bank 2 will make both of their $1 or $10,000 increase relatively the same. Okay? No new homework yet. Tomorrow we'll continue here with this exponential stuff. My hope is to have 4.3 posted to Schoology by the end of the day for you if you're a person that prints that stuff off. And you asked about a practice test. So I'm not going to make a new one. I got practice tests from the past. Basically what I'm going to do is just forward you one of those, but tell you, hey, we're not going to see question 25. We're going to see something like question 22. There's some stuff because of the nature of this course this year that we're removing, and we're not going to get to. And I actually talked to the chair of Rhodes yesterday, and she said that the state has come out and actually said that the two topics that we're not going to get to, conic sections and series and sequences, the state has actually eliminated it from college requirements for college algebra. Okay, so you don't need any of it. You see it in algebra too. So that's kind of a good thing. So when we get down to logarithms next week, we'll have the course finalized and we'll be good to go. All right? And series and sequence, if you're worried about, like, well, I need that because I'm going to use it somewhere else, you will only use that in a calculus course. And at that time in the calculus course, they will go through that stuff again. All right?